Okay, in this video, I'm going to introduce the idea of a coset of a subgroup of a group. So let's assume that G is a group. We'll assume that the operation is multiplication, and H is a subgroup of G. And we're going to let A be an element of the group. That's going to be fixed. Now, keep in mind, A can be any element of G, does not have to belong to the subgroup H. And we're going to define something called the left coset, AH, and the right coset, HA. So I'll start with the definition of the left coset. The left coset, AH, is the set of all elements of G that can be obtained by right composing or right multiplying A, that fixed element, with an element of H, an element of the subgroup. So a way to write this set theoretically is to say AH equals the set of all elements expressible as A times lowercase h, where H is any element of the subgroup. Okay, so that's one way of putting it set theoretically. All right, the right coset HA, that is the set. Similar idea here, the set of all elements of G that can be obtained by left composing A with an element of H, an element of the subgroup. So HA, that's the set of all elements lowercase h times A, where H belongs to the subgroup. Okay, and one thing that you'll probably notice pretty quickly here, these definitions are quite similar to each other. What makes them different is which side of A that subgroup element goes on. But if we're in an abelian group, these are going to be the same thing, because in an abelian group, AH is the same thing as HA anyway. But in a non-commutative group or non-abelian group, left cosets and right cosets may be quite different. And that's where quite a bit of difficulty with cosets sometimes comes from. Let's do an example where the group is abelian. So for this example, I'm going to use Z mod 8 under addition. I'm going to let H, so let's let G be Z mod 8, and I'm going to let H be the subgroup consisting of just 0 and 4. We know that's a subgroup because it is closed under addition. Every element has its inverse in there, and this has the identity. And let's let A be the element 3. And we're going to construct the left coset of H for A equals 3. The way I'm going to write that is I can start by writing AH. But really, when the operation is addition, I like to write this as A plus H, because what goes between the fixed element and the subgroup is the group operation. Here, you didn't see it because that operation is multiplication, and I don't usually write the multiplication sign. Here, since the operation is addition, and I usually do write the plus sign, you're going to see that here. So this is going to be A plus H. And in this case, that's going to be 3 plus H, because A, we decided, is going to be 3. That's just the example I chose. There's no reason why A has to be 3. And this is going to be the set of all 3 plus H, all elements 3 plus H, where H belongs to my subgroup. And in this case, since my subgroup is the subgroup 0, 4, this set will consist of 3 plus 0 and 3 plus 4. So my coset is the set consisting of 3 and 7. Just to have a useful terminology for this, I sometimes call this the left coset of H containing 3, since this coset does contain 3. And if I were to construct the right coset, I'll just write this down. I won't do all the steps again. The right coset, H plus A, or H plus 3, I would get exactly the same thing, because I would get 0 plus 3 and 4 plus 3, and that is still the set 3, 7. You get the same thing because my group operation is commutative. All right, let's try a different example. In this one, left cosets and right cosets may not be the same thing. Let's have our group be the group D4, dihedral group on the square. And I'm going to let H be the subgroup consisting of the identity, which does nothing, and the flip over the x-axis. Okay, I know that that's a subgroup because it has the identity. This is its own inverse, so this has its inverse in the subgroup. And this is closed under multiplication. This H is closed under multiplication because I can multiply any combo of two elements here and get something that's still in H. So this is a subgroup with just two elements. There's no reason that your subgroup has to have just two elements. I just happen to be picking ones that have two elements. And let's let our A this time, let's let A be rotation by 90 degrees, all right? And I'm going to construct both AH and the right coset HA. By the way, we call them left coset and right coset depending on which side that extra group element goes on, left or right. So this is the left coset, and this is the right coset. Okay, so AH, that's going to consist of what? That's going to be the set of all transformations of the square that are the form R90 composed with H, where H belongs to my subgroup. In this case, that's going to consist of R90 composed the identity and R90 composed with the flip over the x-axis. Okay, and then my right coset, I'm going to work out what those are in just a moment, but for contrast, I want to work out a little bit of the other one. HA is going to consist of the set of all transformations H compose R90, where H belongs to my subgroup, should be a colon there, where H belongs to my subgroup, and that will consist of I compose R90 and the flip over the x-axis composed with R90. All right, this first set is going to have the rotation by 90 degrees in it because that's what happens when you compose with the identity, you just get the same transformation back. My other coset is going to have R90 in it because, again, I'm composing that with the identity. But what's going to happen with this other group element here, this R90 composed with the with flip over the x-axis? I don't have my Cayley table for the dihedral group handy, so I'm going to have to work this out using my little square toy here. So I'm going to start in the home position. You'll have to just trust me because you can't see me doing this on camera. But I have my home position here. I'm going to flip over the x-axis and then rotate counterclockwise 90 degrees. And I believe that's going to give me the flip over the line y equals x. So that gives me flip over y equals x. You can check your Cayley table to verify that. Okay, do I get flip over y equals x for the other one? Let's find out. Well, I'm going to take my home position. I'm going to start by rotating by 90 degrees. I'm doing this transformation or this composition now. Turn by 90 and then flip over the x-axis. I think this time I get something different. I think I've got the flip over the line y equals negative x. So in this case, the left and right cosets are different. And again, that was made possible by the fact that G was a non-abelian group. Now, that doesn't mean that anytime I have a non-abelian group, left and right cosets are going to be different. It is still possible for them to be the same, just they weren't in this case. When they are the same, well, that's special, and that's something we'll talk about in more detail later.